Good afternoon, everybody. Thank you very much, Thais, for being here with us, for accepting the invitation to be here with us. It's a pleasure for us to have you here. So, Thais is a professor of our program. Thais has PhD from the University of Warwick. In the last year, this is from September 2019 to last August, she was a research fellow at the Applied Statistics and Risk Unit at the University of Warwick. So Thais is a young researcher and very productive. And for me, it's a great pleasure to have you here, and for everybody, I imagine. So thank you very much, Thais. Thank you, everybody, for being here with us. So Thais, now you have the word.
Okay, thank you. So I firstly, even though I prepared the slides in English, I first planned the time speaking Portuguese. So I have to speak in English, and probably I'll take more time to speak in English. So let's hope I can get to the end of my slides. So today I'm going to talk about a Bayesian network-based approach for the Brazilian birth care system. So if I was going to talk about regression or Gaussian processes or time series, I wouldn't have to give too much detail on the basic stuff. But since I'm going to talk about a methodology that's not so familiar to everybody, I'll have to give a bit of background on the methods. So even though I tried to summarize it, there is a bit that I have to talk about. So just basic definitions. This work is a joint work with Jaqueline Torres. She's researcher at the Institute of Health Improvement Africa region. Even though she's Brazilian, she's trying to improve the birth system in Africa now. She has done it in Brazil before, and now she's doing it in Africa. And Maria do Carmo Leal is a professor at Fiocruz, a researcher, and she's actually a doctor, but she's doing public health now. So she's the main researcher from this area, let's say. Rosa Domingues and Tatiana Leite are also researchers at Fiocruz working this project. I'll give some introduction on the problem itself, the birth care system problem in Brazil, which is a huge problem, public health problem. Then I'll give a brief introduction on the decision support system that we are working with, or that we are proposing and introducing in this field. I will also talk about probabilistic graphical modeling and how we use Bayesian networks to try to find cause relations, right? So we actually want to do causal inference, not just fitting a model. We can actually interpret the effects as causal effects. I'll talk about the birth network that we have constructed in this project, and also some ongoing steps that we are, some ongoing research that we are still doing. So this is still a work in progress. It's very recent, so it's not complete. Okay. About the birth care system problem, we are investigating the high rates of cesarean section. So it's the surgery we do to give birth, right? And this rate is really high in Brazil. It can be 88% in the private hospitals, and rates that are over 10 to 15% are considered risk for the population. Okay, so we are talking about much, much higher than the limit that is suggested by the health organizations, right? So it's in the private system, it's even worse, because if you look just at the public hospitals, we have 43% average, and in the private sector, we have 88%. In South America, of course, it's influenced by Brazil, so it's 42%, and in the world, it's 20% on average. What happens when you have high rates of C-sections? You have usually correlation with maternal death, morbidity, and near death, when you almost lose mother or child. Also, there is a correlation between metabolic syndromes, diabetes, and asthma in the child. So it's very hard to prove this kind of effect, but there are many studies that indicate that when you do a C-section instead of a natural birth, you increase the chances of the child to have this kind of syndromes, diabetes, and asthma. In Torres et al., that's the collaborator for this work, she does a complete review and propose the theoretical model for the birth system. Okay, so this was a PhD thesis in the health and public health field. Okay. In developed countries, the maternal death rates are very low, but this is not true in Brazil or in underdeveloped countries and developing countries. And for that to change, we need to change the birth care system. So you have to make improvements in the system so that you can lower the rates of death and near miss and diseases related to the birth. So in this work, the goal is to use expert judgment to estimate the birth network for Brazil. And this can be used to inform decisions of policymakers and can be used as a tool to prioritize investment. So if you are in the context of low budget for improvements in the health system, you have to choose some aspects to attack, right? So this tool is aimed to help the policymakers to make decisions. So prioritizing what's more important in that moment to be changed to affect the outcome of interest. So how does it work, the birth in Brazil? Why is it so bad in the context of public health? First, we have the birth as a business, and that's wrong, right? So the birth should be decided depending on the clinical conditions and not on making more money, right? So that should be the logical behind, but it's not. So here, first, there is the medical convenience. So the doctors earn more money if they do the C-section. This culture of having one only doctor that takes you from the beginning of your pregnancy to the end, when you get to have the birth, the actual birth. So it's the same person making all the decisions and not a team, because if you are going to choose the outcome, the kind of birth you're going to have, depending on clinical conditions, it shouldn't be just one person making the decision. It should be a team with nurses, midwives, and the family, everybody involved. And that's not usually the case. There isn't usually nurse, midwife, assistant. And in the countries that you have more, in some countries like in the UK, you have actually nurses doing the actual birth, helping the birth, and you don't even need a doctor. In these cases, you have very low rates of C-sections. You also have the socio-demographic information, which is very important because depending if you are single or married, if you have low level of education, it can influence the outcome. And also the clinical conditions. Some doctors will tell that you should have a C-section because you have a clinical condition or because the baby is not in a position that should be, and not always it's true that the only solution would be the C-section. Is it okay so far?
Oh, for me, it's okay. Some questions for Thais?
No? Okay, so here is something that I got from the paper Torres et al. 2018, where you have the theoretical birth care system. Okay, so these are, in the second column, you have the driving factors. There are 4 main driving factors, which are kind of a group of variables. It's not just 4 variables, it's just a group of variables in each of these driving factors. Okay, so governance, for example, it has to do with the payment of doctors, how is the hospital working with the doctors, how it's providing information and things like that. The second one is the participation of women and families. As I said, it shouldn't be the doctor the only person making the decision. So information for women and family is very important. So campaigns, birth plan, involvement, etc. The third one is reorganization of care. So you should have a structure that allows you to have the natural birth or the vaginal birth, okay? And this means protocols and rules from the hospital so that the doctors have to follow these rules. And monitoring is like you have some aims, for example, low rates of mortality, things like that, that you should advertise to doctors and families, and also that you aim to change over time. So you should meet regularly with the team to tell the team how good you are doing, if you are having too high rates of mortality or too high rates of complications in the birth, things like that. So monitoring what's happening in the hospital. So there are also confounders, there are external pressure from politicians, etc. So the network, the theoretical model itself, what I'm showing here, is quite complex. It has many things affecting the result, the outcome. Okay. So the data we have from this study is actually coming from a project that aimed to change what was happening in 12 private hospitals in Brazil. So the team went there to actually change how they were doing things. So try to teach them good practices, so employ new rules and things like that. So the director of the hospital was the person to actually negotiate and change the rules and make some things mandatory and buy equipment, things like that. So it's actually a change, an intervention in the 12 hospitals. And after that, this was a project funded by Melinda Gates Fund, and aimed to reduce the C-section rates, okay, over time. And this was done in 2017, 2018. And they have, from this intervention, an evaluation. And this evaluation means that they collected data from 1,800 women. And the data is 330 questions, 433 variables from the woman. These first 330 questions from the hospital. So the director of the hospital, the doctors, they were answering these questions. And also from the woman, we had a form, very long and very detailed, and also clinical data. So first, if you were to think about doing a regression with that, I don't even know how to start. Okay, so I just know that my outcome, one of the main outcomes that I want to study is if the woman had a C-section or not. Okay, that's one of the aims. But how do I don't even know how to start thinking about regression in this context, right? So it's just too many variables, too many confounders, many variables that are correlated with each other. It's quite a complex problem. what's our solution? If regression is not the way to go, what should we do? We're going to consider a model that allows for expert knowledge to be input in a model. So I want to know what these experts in the field know about this theoretical network. They actually have an idea in their mind about how these variables relate and how they are important to the outcome. But it's not a mathematical construct. It's just some ideas that they tried to implement in the intervention. So there are many variables that they know that are important. For example, you should have a room prepared for the natural birth. You have to have equipment. You have to have nurses that have to be trained, things like that. So they know many factors that are important, but they don't know how they relate to each other, and they don't know how exactly they affect the outcome. So we want to accommodate all that. We want to accommodate the non-linearities, the complex cause-effect relations, and also the knowledge of the experts, because they are trying to change the way things happen here in Brazil for quite a long time. They have expertise for that. So the data we have is, as I said, data from 4,800 women for 12 hospitals. We have qualitative data as well that we are not using so far, but can be used in the future, that are interviews with the managers and things like that. So for this work now, I want to use the knowledge from the experts and also the data to try to not explain the outcome, but to understand what's causing the outcome. It's not just fitting a good model, it's trying to understand the cause-effect relations. So the first thing, who is an expert? An expert is, according to O'Hagan 2006, is someone who has great knowledge on the subject. And for this, I have selected some experts to work with, and we have in the team 3 doctors, 1 nurse, 1 nutritionist, 1 biomedicine professional, 1 patient, because the patient is one of the targets of the international protocols. So the woman has to be taken into consideration, and her satisfaction is actually one of the outcomes. Okay, so they advise that we should have women participating on the modeling as well. And I was the facilitator statistician doing the elicitation and also the modeling. So here, the photos in this slide are just the meetings we had. So there is a way to construct the model, and in these, the experts are used to give information about the structure of the model. And in this case, I asked them to divide themselves in 2 groups, and they thought about the relations between the variables and which were the main variables in the model. And then we put the 2 groups together and tried to come up with one network. And after this first meeting, workshop that we worked the whole day, we had many meetings, more than 10, trying to refine the model to make it more detailed. And how do we make decisions under uncertainty? How am I going to give a tool to a policymaker depending on the mathematical model that we are trying to construct? So we have many factors, and we have policies. So policies are interventions, decisions that you might have at the end that you want to do in the future, for example. Let's say buy more equipment or hire more nurses, things like that. So decisions that a director of a hospital has to make. And what's the intuitive solution? We have utilities for the outcomes. So let's say I want the rate of C-section to reduce. This is an aim. I want woman satisfaction. I want low rates of child death or mortality of women as well, things like that. And I can try to give a prize when these things reduce, and penalize when you have a bad result, right? So in this case, we try to compute posterior probability of events and posterior probability of utilities for these events, and then we maximize the utility. That's the way we recommend an action, okay? So in this reference here, Tversky and Kahneman, 81, they say that they have shown that people usually do not make decisions that maximize their utility function. So let's say you know that it's a complex problem, you have many variables, many confounders, and you ask a policymaker to make a decision. It would be much easier if you give them numbers and say, pick the highest one, right? Instead of just giving many options to decide. So the tool aims to do that. So you actually at the end have numbers and you choose the highest one, and this is the recommended action, right? And why, in this case, we are using Bayesian networks to do that. And why Bayesian networks? Bayesian networks are graphical models that represent causal interactions among several variables. And we use the rule of divide to conquer. So you get a big network, a big graph like this one in the left, and you try to divide it in simpler ones. And the model is done in the simpler parts. So the model tends to be simpler than the joint model for the whole graph. For the several variables, the joint model. So the motivation, I'll try to just give a brief motivation why this is useful in this case. So let's say that because we are trying to model causality, so I'll just give you an idea how this would work. Let's say I'm organizing a conference and I have to decide on the lunch menu, okay? So I have to decide how much I'm going to buy of each kind of food so that I don't have spare food at the end and there is food enough for everybody in the conference. So I simplified my problem. So I have a first decision that I give to the participants, that's to decide between beer and wine. Then I have a second decision that's after the first one, that's decide between pork and fish. And then I have a last decision that's decide between salad and cake. So I can construct the network. That's the one I'm showing in the bottom. First, I decide the drink, then I decide the main course, and then I decide the dessert. And it's done in this order. You don't know what's the option of the dessert before you have decided the main course. In this case, it's known that around half people will choose beer and half people will choose wine. From experience, I have organizing conferences. But also, if you have decided for beer, usually people decide on the pork for the main course. And people deciding for wine usually decide for the fish. So you have conditional probabilities that are different. If you decide first for the beer, you have 75% of deciding for the pork. And then if you decided for wine, then you have 25% of deciding for the pork, to have this as the main. And the same for dessert. It depends on what you chose for the main course. If you had pork that's fat, you say, oh, okay, I can have a cake now. I should have salad now. And if you decided for fish, well, it's very light, then now I can have a cake that's more fat. So these are the conditional probabilities. So the conditional probabilities are based on the order. So there is a cause effect. You are deciding more often for pork if you decided for beer first. So there is a causation. And that's what we are trying to do with the model for the birth network. There are a sequence of decisions and events that happen in a certain order and with certain priority that takes you to the outcome. Okay. Okay, so this here is just a statement that translates that, right? So if you have the decision about dessert C, dominantly depends on the decision about main course B, and it's conditional independent on the decision about the drink. That was the first one. Okay, so when I'm deciding about the dessert, I don't care anymore about the decision I had for the drink. So when you estimate the probabilities for this problem, you have 8 probabilities to compute. Okay, so you had just 3 variables, and you have 8 probabilities to compute. If you had 30 variables in a network, which is very common, and each one was binary, which is not my case, I have many categories for each variable, I would have more than 1 billion probabilities to compute, okay, in the joint model. So it's very time-consuming. The complexity here is even larger than binary, so it would be even worse.
Sorry,
so yes.
We have a question in the chat from Guilherme.
Okay.
What happens if you change the orders?
Okay, so if you change the order in a causal network, it changes the solution. So what we believe is that if you put expert input to construct the network, and you believe in this network and the causation you are assuming, that's the solution you get. If you change the network, you have a different solution. So you would have a different recommendation at the end. So the order matters. Okay, so the structure of the graph affects the result. I hope I answered. So the basic stuff, I'll just talk a little bit about that. So a graph is a mathematical construct that will represent these conditional independency statements that I just talked about. And we are going to consider in particular directed graphs. So we have arrows representing the relations, the causal relations. And in particular here, I'm going to denote V, the vertices of this graph, and A, the arcs. They are always directed arrows, right? And the Bayesian network model will assume that the vertices are actually the variables that we are using in our model. So I'll call that Y. And the two variables are going to be conditional independent given the parents of this variable yi. That's what's written here. So let's say I'm talking about node A. It's conditional independent on the variable G given C, because C is the parent of A. Okay, so I just need to know C to estimate parameters related to distribution of A. When you build a graph like that, you have many conditional independency statements. What's the Bayesian network model? The Bayesian network model has 2 components. The first component is the graph. Okay, so this is talking about all the conditional independencies that I'm assuming. And the second component is the local distributions. So depending on the nature of the variable, let's say I have a continuous variable, I could use a Gaussian model for each node. If I had a discrete variable, I could use a multinomial model. If you have some nodes that are continuous, some that are discrete, you have a mixture of Gaussian distributions. So these are the 3 most common approaches, okay? Let's just see if I talked about everything. Okay, here on the first equation, what I'm using is the conditional independence. Given the parent, which is YPI, I have the product here for all the variables. And it's conditional on the graph, as Guilherme said there, if the order matters, if how I construct the network. This is represented by the first component, that's the graph structure. And it's this G here that I'm putting the notation. So this is preferable to using the joint model. That's the one in the right. Okay, the one that considers that everybody depends on everybody. So you had to compute all the probabilities. So let's see how I'm doing the time. So I still have 20 minutes, right? So the learning is the estimation of the network, which estimating the structure and the parameters. In my case, I'm going to use experts to define the graph structure, and I'm going to use data to define the probabilities. I've done other works where I used experts in both, or you can use data for both as well. Okay, so there are many options. So for the structural learning, that's you have to find the minimal map that represents the dependence in the data. Okay, and with that you can actually infer causal effects. So it's much more than regression, because we can actually talk about one variable being a consequence of another variable that's the parent. There are many rules here, many algorithms to do this estimation using data. I'm going to use elicitation via expert knowledge. So the manual construction using expert knowledge has many rules. You have, for example, divorcing of the parents. You have to test many things, the ordering of the variables, but I will not have time to explain how to do it. Okay, so I get to the result. The parameter learning is a bit simpler in a way, because you are modeling each variable conditional on the parents, and for that you have multinomials in the discrete case and Gaussians on the continuous case. So the inference for each variable is simpler, and you can do it in parallel. So you can divide the task in many processors, and you can do it very fast in a way. There are limitations for that, but it's better than doing the joint estimation. So it's the divide and conquer idea. For example, I'll just give an example of estimation, the complexity of it. If you have this network here with 8 variables, you have 255 parameters to estimate the probability tables. If you do the Bayesian network, you have 18, right? So the complexity is much smaller than in the joint model. So the model I'm assuming for that network is the multinomial. So conditional on one value for the parent, let's say I'm talking about one level of the parent, I have a multinomial distribution with a parameter theta, and this parameter is going to be estimated by data, using data. Okay. So if you assume that the prior is Dirichlet, then you have the posterior also Dirichlet, because you have conjugacy, right? So for each node, you have the theta and the thetas, because you can have many multinomials. And this parameter is Dirichlet a posteriori. Okay, so it's you have closed inference for each node. And this is guaranteed by some theorems. So you have global independence and local independence. So let's say I have a parent with 2 outcomes, 2 levels. So the child has 2 models, one multinomial for one level of the parent and another multinomial for the other level. They are independent. Okay, so this is local independence. Then you have global independence. If you are talking about one level of one parent for this node and another node with another level of his parents, then you have independence as well. So it's all independent. This is because of the conditional independence and the Dirichlet assumption as well. So all these together give us scalability. Okay, so this is the main paper doing the Bayesian inference for this model. For the simplest case, the discrete with no temporal evolution, but it's very well written and has many details, proofs, everything. What we want to do here is to make decisions. So we want to do predictive analysis. That is, I'm going to compute a utility function at the end. And this is based on the posterior probability, on the marginal posterior probability. That's the prediction. Okay. And for that, I'm going to do what we call query analysis. So what we do, we fix a value of a variable in the network. Let's say I don't want anymore to allow for scheduled births. So you cannot just tell me a date you want to do your birth. You have to wait for labor, okay? It could be a rule from the hospital. That's one of the variables. If this is a rule from the hospital, then everybody has to follow that rule. And if you change that variable, what's the impact on the outcome? That's the predictive posterior distribution for the utility function at the end, when you look if the birth was cessation or not, okay? And what you are fixing is called evidence. So you give an evidence and you fix it. It's hard evidence. I'm going to change everything. So everybody in the hospital is going to have to follow that rule. And with that, I can see how it impacts the result. And for that, to compute this predictive distribution, as I said, it's the computation of probabilities has a lower dimension than the original problem, but it's still very hard. Okay, it becomes very large, very quick. So instead of doing the exact predictive distribution, we do approximations, and these approximations done through logical sampling. Okay, so I will not have time to detail that. So in this analysis, after these workshops and these meetings with the group, we came up with 24 variables that are essential for the network. And we came up with these relations. So this was labor-intensive, many meetings and many discussions with the experts. And there are many rules and protocols that guarantee that this can be interpreted as a causal network. Okay, so you just have to follow the protocols. And at the end of the network there in blue, you have the two outcomes of interest. That's the type of birth, that's either cessation, vaginal, or you had labor but still cessation, okay? And the age, the gestational age. So let's say 40 weeks, 41 weeks, that's also important. And here is one of the factors that they define as important. So you can group the variables in the 4 main factors that they have in the theoretical model. Okay, so this is governance. So it's like changing how the doctors are paid, for example. So you have there in the 12 hospitals a different way to do it. Okay. And participation of women in families, so you have all that, how they changed everything, so it's reflected there in the network. Also the reorganization of care, so how is the protocols, how they do the labor, what kind of anesthetics they use, things like that, also represented in this part of the network. And you have the monitoring variables, that's the indicators that they are collecting and presenting to doctors and women and everything. And the confounders, so you have a woman with risk, they usually, if the risk is high, they usually have cessation. So you have to take that into account. And here are some results. I have, I don't know, 5 minutes, Kelly?
I think 10 minutes. Is it okay for you?
Okay. So here I have just one example of conditional probabilities. This is for the variable early admission. So I just got one of the variables here on the network, and I'm just showing you the subgraph. Okay, so the early admission, that's the one in the bottom, depends on the model of the team and also on the schedule of the birth, if it was scheduled or not. And here you have the probabilities. You see they are very different. So there is actually a difference between the levels of the parents. So this indicates that it's actually something that should be included in the model. For example, if you have your birth scheduled and you have one doctor responsible for everything, is the one in the bottom in the right, it's most almost probability 1 of having a C-section, okay? So here is no labor, probability of no labor. And if you have the team from the hospital doing the birth, and you are not scheduled for birth, then this probability is 60%. No, of no labor is 26% instead of 0.99. So it's very different. Also here showing another node that's more from the driving factor responsible for women and families. And here is if the woman was motivated to join a group of women to discuss the birth. And also there is a difference if you are doing it, if you are receiving this information from the hospital, you can see that the probability, if it was offered by the hospital, let's see here. So the incentivo de grupo, it's in Portuguese, but it's if the group was, if the information comes from the hospital, the probability of the group being offered is 79%. But if you are getting your information from outside, then the probability of joining the group and having a group offered to you, it's lower. So the hospital should be doing this job. Here is the posterior distribution, for example, for one variable that's labor. Labor is very important to actually have something different from C-section as outcome. And if you are scheduled for a labor, the probability of having labor is less than 20%. But if you are non-scheduled, this probability is almost 70%. So it's very different. Okay. And if you don't have labor, the probability of vaginal birth is 0. So it's a very important variable. How we compare policies, as I said, I'm going to use maximization of utilities, and I use logic sampling, as I didn't have time to describe it, but it's a Monte Carlo simulation, basically. And here, I just, to illustrate, I'm showing you 5 policies. So one is good, is the first one, is setting some variables to very good levels, okay? And the last one, that's policy 5, is setting the same variables to bad levels, non-recommended levels. And the 3 in the middle are in between, just improving one aspect of the network. So you see that these illustrate how different the actions are. And the next step is to consider how the hospitals in the study, the 12 ones, are doing in this range, okay? And to test all the variables, 1 each time, then 2 each time, to see in a graph which ones are the actions more recommended if you have budget to change one thing, for example, right? So you have the most important decision that you could make with a low budget, let's say. So one ongoing work that I'm going to talk about, just I extended this model to time series, so that if you have a study that's followed over time, the probabilities can change, mostly after interventions, right? So you make an intervention, you expect it to change. So if you are following the probability over time, you should put some structure. And for the continuous case, there are many proposals using Gaussian processes. They are famous as conditional Gaussian processes on the network. But for the discrete case, there is not much done. And I have proposed one theorem that does automatic filtering and smoothing. So it's possible to do it very fast. So it doesn't increase complexity, but allows you to analyze time series as well. And also, so about the funding for this project, as I said, the study itself was funded by Bill and Melinda Gates, and the partnership to do the policy evaluations and recommendations was funded by this EPSRC accelerator account. Okay. that finished in August. And here are some references. The important one, as I said, the first one is very important. It's from 95, but it's one of the basic ones. And this one, the third one from 2007, is trying to do a logic sampling a bit more advanced in the sense that it allows for full Bayesian inference, but it's just for binary data. So I want to do it for general cases. Here is another network that I've done for food security, that's hunger. And another project that I have is doing that for Brazil. So you have many economic variables that cause food security. So that's the outcome, right? And you have experts deciding what's important in economic sense and social sense as well. So that you have groups of experts with expertise in several areas. It's not just one area, okay? And that's it. I finished.
Thank you very much, Thais. It was a very good presentation. And my particular case, it's a topic totally new for me. And it seems to be very interesting and very relevant in your case if it's your data set. So thank you very much. Do you have questions?
Vocês podem perguntar em português também, tá, gente? Eu posso traduzir aí pro pessoal.
Yeah, sim.
Thank you, guys, that came today. Any curiosity, doubt, suggestion, criticism?
I think we have one here.
Okay.
Okay, so while people are thinking about your question.
Okay, there is one question here, Kelly.
Oh, yeah?
Ken Kitson. Will you be able to do the interventions you recommend in real life to see if your model is accurate? This project has got a second grant, so it is now going on field to check how the interventions are doing in these 12 hospitals, right? So it's something that's still happening. So there is space for us to recommend interventions and follow it over time, right? So there is space for that because these people doing the interventions in the hospitals, they have the agreement of the directors and the managers, and they actually change it like equipment, the rooms and the staff. It's something huge in these hospitals. So if you recommend an action and if the conclusion of this study is that we should be doing this kind of action instead of this other one, it's going to be on the paper and they will apply on the field for the next interventions. This work is going to be in a special edition of a journal, and there will be 2 papers there, one describing the network and another one talking about the interventions. So it's probably something they will use in the future for future interventions, I believe. Are there any rules to choose the number of childs? Yes, there is. As I said, there are many protocols to construct the network. And for example, if you put a child with many parents, so you say that many things are influencing that child, you get too many probabilities to compute. So it gets too complex. So in this case, you do divorcing, for example. It's one rule to do that. You create a latent variable that's usually deterministic that simplifies the effects. So you have less parents. So there are other rules for less child as well. So you can simplify. You are aiming to have simpler explanations, right, in the subgraphs. So you shouldn't put too much complexity in one part of the model. So there are ways to simplify, to have less parents and child. I like to know the number of tests based on interventions. you gave different combinations of intervention. If one combination of intervention has been tested 1 or 2 times, that may not be convincing. I'm not sure if I understood. Or the sample size of the based on interventions. Let me see if I understood. I'll read the question again to see if I understood. I like to know the number of tests based on intervention. You give different combination of intervention. If one combination of intervention has been tested 1 or 2 times, that may not be convincing. Well, about the tests and the interventions, there are nodes that are nodes of decisions. So these are the ones you want to change, right? There are some nodes that you cannot change. For example, the clinical conditions of woman, you cannot change. Or let's say that the hospital has a certain kind of number of rooms for natural birth, and it's fixed. Then you cannot change. But then you can change the protocol for labor. So that's a decision node, and that's the one you are going to test in your test. So the number of tests is already limited by the ones that are nodes for decision. Okay, so it's not the whole network. The next step from the plot I showed is to show a plot, is a bivariate one, where for decisions, for interventions change 1 node at a time, you see what happens with the 2 variables, the outcome variables. And you do that for all the variables 1 by 1, and then 2 by 2, 3 by 3, and then you see the results of the interventions. I can show you if, let me just stop this presentation and see if I can show you another thing here. Let me see if it's possible. I don't know if I can do that. A window. No, I'm not sure how to show one window here.
You are presenting in the screen.
What can you see?
I think it's your email, something like that, but it's just the...
Okay, no, so it's not what I wanted to show.
So you want to share a document?
Just a window in my computer, in my Mozilla. Let me see if I can. Can you see anything?
Just a minute. Yeah, it is. Please wait.
Okay. So that's what I want to show. Just a minute, because my internet is very slow now. So this is another project where we did this elicitation of the network and the policies and everything, and this is complete. So I can show you what happens next. So you do, after defining the nodes, that's what we have done already here in this project. You create your model. So the model is the network. Let me show you here in the definition. I have here the network. And then you, in this case here, I have some inputs. So the person using the app can put some probabilities here as well. So it's more personalized. And then you have recommendations. In the recommendations, you choose the model that you are using, and you do recommendations. So the one in the top right are the ones that are best. So after creating your policies, you can compare several policies. And you have the number here as well for model comparison. So telling you which the best decision, let's say, so it's ranked. So the comparison of policies, you can do this plot like the one I showed with 5, I can do with 10 if I have 10 policies, okay? And the recommendation one actually shows you all the tests we have done in the app. So depending on the decision nodes, you do all the possible tests. And then you have a report. So this is a complete decision tool. So the policymaker can go here and test different actions and make the best decision according to maximizing the utility. So it's something complete in a way. They can actually use the app. Another question, also, would you consider learning the Bayesian network structure from data and comparing with the... That's what they asked me the last meeting, Ken. The doctors and the nurses, they asked me to actually do the estimation of the structure and see if they are right. So, well, I prefer their input than using an automatic method, but I'll try that because they are curious. But I don't think it's the way to this context. I have not done yet, but I'm curious as well if they are that good in deciding on the structure. But I believe so. Maria do Carmo, for example, worked for more than 40 years with that. I don't believe the automatic method is going to do any causal inference better than she does. So
I have fun.
You mentioned 433 variables at the beginning. What are those variables? Yes, I can show you. Well, there is a form for the manager of the hospital. That one has 300 something questions. And these questions are, how many doctors do you have for specialized in obstetrics? How many nurses in the hospital? How many rooms for natural birth? How many balls that the woman can sit on top of it for the birth, and things like that. So it's really detailed. And the experts know which is more relevant, right? So I don't use the 300 something from the manager. I use a few of them that the experts have chosen. And from the woman, we have everything from the woman. Clinical records. So these 433 account for clinical records. The interview was done 6 hours after the birth, asking everything. How do you feel? Are you satisfied? Did you take a shower? Did they give you anesthetic? Could you walk? Did you have? Did you take any medicine? Were you respected? Things like that. It's like really detailed and planned. They planned it very well. It's like there is a protocol, and the nurses to applying the questionnaire, they were trained before for the study. So it was very well done, even though it's very big. So I'm not sure how the woman take that 6 hours after the birth, but they do. And they did it for 4,800 women. So it's really a big study, and it's really substantial for our system here. And the people involved are very serious, and they want to change the system. So they have in the same hospital, they have the pilot is the population where they are doing the intervention, and they have the ones that they are not doing the intervention. So it's separated, and they can test if it's working because of the hospital or not, right? Because then you have the same at the same hospital, the woman that have the intervention being applied and the ones that don't have. There is some contamination, but the effects in the pilot group is much larger than on the other group, right? Yes, any other question? Curiosity, suggestion?
Yes, Thais, if you don't mind, I understand that you already explained that you actually didn't use data to learn the structure of the Bayesian networks. You just use expect knowledge. And I wanted to know if you had any structured method to do that, because we are working with the same in Queen Mary, and one criticism that we have been facing is that we don't have a method to actually elicit these structures.
Mariana, that's a very good question. There is a method. I'll give you the reference now. Just 1 minute. I'm not sure I put it in the slides, so I'll just open it now here. And the thing is, they call it, there is a name for it. For example, let's say you have a child and many parents. So usually that's what happens. The expert tells you that many things are affecting that child. what you do, it's a method called divorcing. Okay, so for all the things that you have in practical elicitation, you have some solutions. So that's the kind of protocol you have to follow. And there is a chapter in a book about decisions and Bayesian inference that tells you some rules to guarantee you have an actual causal structure that makes sense and it's not too much computationally expensive. Because if you just put relations arrows everywhere, then you go back to the joint model, right? So you should have some structured way to do it. For example, there are 4 kinds of variables. There are variables that are decision variables. There are variables that are confounders. So first you can, when you define the variables that you are going to use, you can categorize the variables. Which ones are decision, which ones are chance variables. So after this categorization, this is already one step of the construction, you have a kind of an order, temporal order. Some things happen before the others, right? So you can also use that. So that's another aspect. Some variables have to happen before for something to happen. So there is a causal structure, and you should use that as well. And for example, if you have a decision node, you cannot be a confounder. So there are some rules that you have to respect so that at the end you have a network that makes sense. And in a way, the people that criticize your work are right, because we do a lot in using intuition, and the experts know a lot, so you want to respect their input, but you also have at the end to check if all the rules that you should follow were followed, right? So I'll give you the reference. I can send you by email later. It's a book. There is a whole chapter explaining. It's based on empirical, practical work. So if this happens, what should you use as a rule, right? As I said about the divorcing, right? But it's a protocol. For me, it works as a protocol.
Yeah, all right, thank you. And I wanted to ask you if, as these people that you're working with, they are not actually computer scientists or they're not people that actually are familiar with this, how do you check if they are happy with the model you built?
Okay. So the ones in this project, the birth network projects, they are in the public health sector. They usually know a bit of a regression and DAGs. Some of them understand DAGs. So they, after doing the workshops with the experts, let's say 10 people, 20 people, I keep having meetings with some of them, and they tell me if the network makes sense, okay? Because we put more detail, when some variables, when I try to use the variable, they don't make sense because the variable was not well collected. So some variables were removed because of that. So they find one to replace it. And so it's a bit interactive. I show them, and then they give me another way to go when there are problems. And at the end, sometimes they want to change something after we have decided the network. And I say, well, let's fix this one for now and test it and do the recommendations. And for the next analysis, we change, because they are very creative and they want to put more variables. And so I also have to put a limit on the time. But for the other project, the diagram, we had also workshops of, let's say, I don't know how to call it, but for them to see the results. And then they told me what is not right, what's wrong. So it's evaluation, kind of evaluation of the model. And we have also testing, user testing for the diagram, the app. We actually run sessions. It's open to everybody working in the field, where users test it and evaluate at the end and see if it's making sense, right? So that's a way to do. So it's user testing, because it's actually complete. It is an app online that they can access, and they change, they put the inputs and they do the policies and they see if it's making sense. And then they write a report making recommendations of changes and improvements. And this diagram that I showed you here has changed a lot after the user testing.
Yeah.
Okay, so we changed
did you,
even the network. Yes?
What tool did you use to, just the last question, what tool did you use to build the Bayesian networks? Did you use
I used R. To do the fitting, I use BN-learn. Okay.
Yeah. And
for the full base that I'm working now, I have to code it. So I'm using parts of the Marco Scutari code. So it's open source, right? So you can get it and use, and so it's really good. For the diagram app, it's actually R as well, the one I showed you. It's R. It's surprising, but it's R. It's Shine, R Shine.
All right. Thank you, Thais, and thank you for giving the presentation in English.
No problem. You are welcome, and please come again at some time. So, yes, very good questions. Thanks a lot for the questions.
And have some comments, Thais, in the chat, so you can see there.
For the similarity that feel constant, we can learn for other variables. We can learn from data. Yes, you can do inference based on elicitation or data, or both. Actually, you can have some nodes that are listed and some nodes that have data. So for the diagram, the one that I just showed, the app, we have some nodes that the probabilities are listed by experts, and some nodes that are data. We had data. So the probabilities are estimated based on data. And for the structure, yes, the structure is something that I was in the next step of this project. I want to test, make some hypothesis testing of some errors, some, let's say, some relations. The basic network is the one that the expert made, but then I can remove and put back one error and see how the recommendations change, or how this error was important for the network. So do kind of a hypothesis testing for the relations. So it's confirming the causality, let's say, but one at a time or two at a time. Very good. Yes, it's very good package by Marco, and it can learn structures. That's why I told that to the experts, and they said, "Oh, so run it, please." So I'll do it, but I haven't done it yet because of time. As you see, to just come up with the network, it was like from February to October. So quite a lot of work just to translate what they think to the network. So it's not an easy task, but it's a very, very nice work to work in a team like that.
Okay, so more questions for Thais. I just have a curiosity. I think I may be lost in some time. Did you use the data from public and private hospitals in your application?
Just private. This PPA, that's the intervention, was done in 12 private hospitals. There was a previous study in the past for the public ones. So it was separate, because the decisions are very different, and the structure is very different. The variables affecting the network are very different. So for now, we are doing separate, like I'm doing just the private, but we have data for the public as well from a previous evaluation.
Okay. So if you use the public, also you can also have to change the 24 variables that you use in your network. They may be different in this case.
Probably different.
Okay.
Yeah. The private hospitals change the structure easily because it's just the manager putting some money, and the public one cannot be like that, right? So it's the network can have similarities, but the actions are very different. The the recommendations would be very different.
Yeah, makes sense. Okay, so if you don't have no questions anymore.
Suggestions, so recommendations, criticism.
Okay, so let's thank Thais. Okay,
thank you for
thank you very much.
Good to see you.